humanity has cataloged over 6,000 worlds orbiting distant stars. To find life, we have to narrow that list. The first filter is composition, isolating rocky planets like our own and discarding the massive gas giants. The second filter is distance. We look for the Goldilocks zone, where a planet is far enough from its sun that water doesn't boil away, but close enough that it doesn't permanently freeze. Even when we find a rocky world at the right distance, one variable has remained out of reach. Until now, we had never confirmed the presence of an atmosphere around a planet like this. Without an atmospheric shield, the surface is a dead end. Liquid water would instantly evaporate into the vacuum, and the ground would be sterilized by a constant stream of high-energy stellar radiation. Confirming an atmosphere is the final, most difficult filter in our search. It's the difference between a sterile rock and a world that can actually maintain the conditions for life. This search led researchers to LHS 1140b, a planet 49 light-years away in the constellation Cetus, orbiting a small red dwarf star. By measuring the gravitational pull on its star and the shadow it casts during a transit, astronomers calculated its size. LHS 1140b has a mass 5.6 times that of Earth and is 70% larger in radius, but its environment is hostile. Red dwarfs are notoriously active, frequently blasting their planetary systems with extreme ultraviolet radiation. This radiation typically acts as a cosmic sandblaster, stripping away the outer gas layers of any nearby planets and leaving them airless. LHS 1140b is a test case for survival. If it holds an atmosphere here, it proves that rocky worlds can remain habitable even under the galaxy's most violent stars. Dr. Colin Cherubim's team investigated this using the Magellan Clay Telescope at the Las Campanas Observatory in Chile. With transit spectroscopy, astronomers watch the planet pass its star. The solid body blocks light, but a fraction passes through the thin gas rim. Splitting this light into a spectrum reveals chemical fingerprints, as gases absorb specific wavelengths, leaving unique dark signatures. In 2024, the team detected a clear signal. A specific chemical signature was trailing off the planet and escaping into space. That gas was helium. Then, in 2025, the signal vanished. The helium was gone, forcing the team to reevaluate their entire dataset to ensure the 2024 discovery wasn't a fluke. They had to prove the helium didn't come from Earth's own atmosphere, contaminating the telescope. They did this by comparing the signal's timing to the planet's exact position. The helium signature only appeared at the precise moment the planet crossed the star, ruling out local interference. Confirming the signal proves that our instruments are now precise enough to detect the atmospheric composition of a rocky world 300 trillion miles away. Helium itself cannot support life. It is an inert gas that sits in the upper reaches of a planet's sky. Its presence, however, is a physical shield. If helium can survive the intense radiation of a red dwarf, it means the planet has enough gravity and stability to maintain an atmospheric envelope. This suggests that heavier, more complex gases, like nitrogen or oxygen, could be protected in the lower atmosphere, closer to the planet's surface. LHS 1140b has changed the search for life from a theoretical exercise into a targeted study. We now have a confirmed environment where we can look for the specific chemical signatures of a living world.